Hello, welcome to day 5 of the neural network series. In our previous video, we've gone through a function, a quadratic function, 3x squared minus 4x plus 5, where we try to extract the derivative of a function so that we could know how much is the function changing when our inputs are changed by some factor. So in today's video, I will be taking it to another level by having different inputs in order to get a predicted output. So let's take three inputs A, B, and C, and let's think that the simple function equation for that is A into B plus C. So this can be said to be these can be said to be inputs and D to be our output. So this D basically, in a very generic and low level sense, uh, let's consider for our understanding as the output of the neural network. So now we would like to know what is the effect of A, B, and C on D, and how much of a change in A, B, or C will affect the D. Because we start with some random weights. Let's suppose A, B, C to be random weights in neural network, and we are going to tune these weights so that the D that we predict is closer to the actual value. So we need to change A, B, and C, or weights. So if we A, B, and C consider to be input weights as an example, as a very low level example, then we need to see how much is D changing. Now let's in order to do that, we need to find the derivative of D with respect to A, B, and C. So if we take inputs and we say if we're going to nudge A by a small amount h, then how much is the function change? So here d1 is f of x and d2 is f of x plus h with respect to A, like h is added just to A. And now we can see the output of d1, which is 2 into minus 3 is minus 6 plus 10, that gives 4. And here we are adding a value to A in a positive direction, but when we multiply it with respect to B, which is negative 3, so the D2 is going to actually be lesser than D1 because A is positive and B is negative, and hence the equation, the output will actually be less than D1. And now if we look at the slope, that is f of x plus h minus f of x, and then divided by the rate of change, we could see that the slope is a negative 3. Negative 3 is essentially the value of B. Now what does this tell? This basically tells that when you increase the slope of equation with respect to A is B, because if you go with the traditional differentiation function, differentiating D or D1 with respect to A is actually this: D by dA is equals to A into B will be changed to 1 into B plus differentiating D by dA with a constant C is going to be 0. So the output is B. That's the reason why we have slope of minus 3, which is actually equal to B. It applies the same when we differentiate the equation D with dB. The slope will be A, and D by dC, the slope will be C. Oh, sorry, the slope will be a constant 1. Yep, is A. And if we do the same with respect to B, where we increase the b to find the derivative, then we could see that the slope is actually equals to a, and now d2 is greater than d1 because b being a negative value has been by adding h to it, we got it closer to 0. I mean closer towards a positive scale, and hence the effect of negative reduces. Now what will be the slope with respect to c? It can be seen that c being a constant in the equation, the slope of c will just be equal to 1. That means if we change this constant, then it goes towards the positive direction with a magnitude of 1. So in this way, we can understand what is the effect of tuning each of these parameters on the final output D. And in the next lecture, we'll be talking about a little more complex function on how to get this D value and calculate it with respect to the expected output to know what the error is. Thank you so much for the time. See you in the next video. Bye.